Hello everyone, today we have the third part of Exam 1 for our Transport 2 class. The situation that we are dealing with is we have a tube with excess air being blown across it. At the bottom of the tube, we have a liquid mixture of acetone and methanol. Now at that liquid interface, we have that Z equals 0. Above that liquid interface is a vapor state. At the top of that vapor state, we have that Z equals delta. Now, we have three components that we're working with. For component 1, we have acetone, component 2 is methanol, and component 3 is going to be air. We have the mole fractions of these. The mole fraction of component 1 is 0.319. The mole fraction of component 2 is 0.528. And the mole fraction of 3, we can find that by knowing that the sum of all three mole fractions must equal 1. And because of that, we can take 1 minus the mole fraction of component 1 minus the mole fraction of component 2 must equal the mole fraction of component 3. We know that delta is equal to 0.24 meters. We have the temperature as 328.5 Kelvin. We have the pressure as 99.4 times 10 to the third pascals. The gas constant is 8.314 joules over meters times Kelvin. We also have the Stefan-Maxwell diffusivities. For 1 and 2, it is 8.48 times 10 to the negative 6 meters squared over seconds. For 1, 3, it is 13.72 times 10 to the negative 6 meters squared over seconds. And for 2, 3, we have 19.91 times 10 to the negative 6 meters squared over seconds. So for the first part, we're going to be solving for the molar fluxes of both acetone and methanol. To start us off with that, we know that diffusion happens in one direction. We know that the vapor from this mixture will be traveling in the positive Z direction, while the air will be traveling in the negative Z direction. We also know that the molar flux of air will be 0, and the reason being is because it will not dissolve in a liquid. It won't be dissolving in this, doesn't dissolve in water, it won't be dissolving in this liquid, so we can assume that it's going to be 0. Now, to work with this, we're going to use the Stefan-Maxwell diffusivity equations, and I'll write those out right here. We're going to be comparing the molar fraction of component 1 compared to the Z distance, and we're also going to be doing the same for the molar fraction of component 2 to dz. So I'll write those out for us. So as you can see here, we have that the molar fraction of component 1 times the molar flux of component 2 minus the molar fraction of component 2 times the molar flux of component 1 all over the total concentration times the diffusivity from 1 to 2. Here we have that added to the molar flux of component 1 times the mole fraction of component 1 times the molar flux of component 3 minus the mole fraction of component 3 times the molar flux of component 1 all over the total concentration times the diffusivity from 1 to 3. Down here we have it that it equals the mole fraction of component 2 times the molar flux of component 1 minus the mole fraction of component 1 times the molar flux of component 2 all over the total concentration times the diffusivity from 1 to 2 added to the mole fraction of component 2 times the molar flux of component 3 minus the mole fraction of component 3 times the molar flux of component 2 all over the concentration times the diffusivity from 2 to 3. I know that was a mouthful, but just to make sure you have it down in case you can't see it, But we can actually also cut out one more part here. We know that since n3, we have written up here, n3 is 0, we can actually cut these parts out as 0. We don't have to worry about that, which is really nice. It's going to cut off a little bit for us. Now, to work with that too, we're going to need to use the equations to give us these equations can, along with the givens can help us integrate and find the initial value problem, the IVP. So with that in mind, now that we have these equations and actually with these givens, we can find the initial value problem, the IVP. But we're not done yet because we still need to find the molar fluxes of both the acetone and the methanol. To do that, we're going to have to take guesses, and by guesses, we're going to be using orders of magnitude. We need to also bring into the fact that the driving force, for the independent variables and the dependent variables, we're going to have that scale from 0 to 1. The order of magnitude will be 1 in that sense. To do that, we're going to have to bring in a new variable, eta. And eta will be equal to the z that we have up there over delta. With this in mind, we can actually put that into here, where we'll have, instead of the y being compared to the z, or sorry, the mole fraction of 1 being compared to the z, we're going to have the mole fraction in comparison to that eta. And then here we're going to have that multiplied by that eta in comparison to the z value. And see, those would cancel out. That's why we can bring it in. It's kind of like bringing in 1 over 1. So, with that in mind, the same applies for the second component right here, for y2, the mole fraction of the second component. With that in mind, we can actually go ahead and replace this with these values, and we can actually bring it in that this will be those, but we're going to replace this value with 1 over delta. And I'm replacing that with 2, but it's for 1 and 2. I'm just not going to rewrite it there. So with this in mind, we can put it over here, but we're going to move that delta over to the right side of these equations. Now I have it on the left. So I'm going to rewrite that right now. Up here, or down here I will. So we have that the y1 in comparison to eta will be equal to the mole fraction of 1 times the molar flux of 2 times the molar fraction of 2 times the molar flux of 1 all over the total concentration times the diffusivity from 1 to 2. And we're going to put that, the 1 over delta, it would be on the top, but we're going to put it down here at the bottom. Down right below that concentration and diffusivity. And this is no longer going to be a plus because we got rid of this, so we're going to put that as a minus from that right side right there, or it's subtracting. And I'm going to have to get down on my knees for this last one, but I'm going to rewrite it for component 2. Now, with this in mind, we actually are going to be finding the orders of magnitude for this. And on the left side here, for both of these, we know that the order of magnitude must be 1. Why? Because this is a mole fraction, so from 0 to 1, the order of magnitude must be 1. And we just found for eta, it is also a fraction of these values, therefore, the order of magnitude must be 1 as well. The same applies here. And with that in mind, we know that the right side must also have an order of magnitude of 1. To find that, though, we're going to have to find all these individual orders of magnitudes for all the different components. We can actually cut off a little bit right now though, because all these mole fractions and the delta, we know that all those orders of magnitude must be 1. So we have 1 here, 1 there, 1 there, 1 there, 1 there. Got 1s everywhere. That is a huge help. That cuts off a lot for us. Now we just have the molar fluxes. We have the concentration and the diffusivities. Those are our only orders of magnitude left over. We actually don't have the concentration, but we can solve for it because we have all of these wonderful given components. So I'm going to rewrite it up here. We don't need this anymore. We don't need that anymore, actually. To find the concentration, we're only going to be finding the order of magnitude for it, actually. We know that the concentration follows this equation. There's the pressure over RT times this diffusivity. So with that in mind, now we have to look to our values that are going to be given here. We know that pressure has an order of magnitude. This is 99.4 times 10 to the third, which is close to 100 times 10 to the third, which is really just 10 to the fifth. So we have this is 10 to the fifth. For the gas constant, we have it as 8.314, which is really close to 10, so we have that as 1 times 10 to the first. So it's really just 10 to the first. The temperature is at 328. We're going to bring that down to 100, which is close to, and that makes it 10 squared. And that diffusivity, we have a similar one right here, same one right here, where it's pretty much 10 to the negative 6th, and 10 to the negative 6th is close to 10 to the 5th, or sorry, 10 to the negative 5th. Because it's 10 to the negative 5th and 10 to the 5th there, we cancel that out. We get that the concentration with these two values at the bottom there has to have an order of magnitude of 10 to the negative third. That's great, we can put those in there, and we have these diffusivities right here. We're going to say that all the diffusivities are at 10 to the negative fifth, because they are all close to that. This is 10 times 10 to the negative 6th, this is close to 10 times 10 to the negative 6th, and this is close to 10 times 10 to the negative 6th. All of those will go down to 10 times 10 times 10 to the negative 5th, I apologize. So, with that in mind, we're going to go ahead and erase this. Actually, we can keep it up, because we're almost finished. We know that the concentration is at 10 to the negative third. We know that this diffusivity is 10 to the negative fifth. This is also 10 to the negative third. This is 10 to the negative fifth. Down here, 10 to the negative third. 10 to the negative fifth. 10 to the negative third. 10 to the negative fifth. And with that, the only things that is left over for us is those molar fluxes. And with all of these components taken in hand, we can actually take those molar fluxes and reduce it down so that the orders of magnitude, we can get the estimates for these, as the molar flux of component 1 is roughly around 10 to the negative third for the order of magnitude. Component 2 is also 10 to the negative third. Looking back at this again, I greatly apologize. I rewrote this 10 to the negative fifth. We were not supposed to be doing that, because we actually had it solved up there. So we don't have to worry about that. That's why here we have the whole block is 10 to the negative third, and the top is 10 to the negative third to make it 1 over 1, which gets us the order of magnitude of 1, just like the left side is. Hello everyone, this is part 2 of the exam. We're going to be actually solving for the molar fluxes of acetone and methanol. We're going to be using Google Colaboratory for this. In the last problem, we found the estimates for them, but we need to now solve for them. So we have this from our last one. Some of them are given, some of them we were able to find out. We have all these values, and they are
change to the units that we will need to use. So we have here too that the concentration, since this is an ideal gas, we have that the concentration equals the pressure over the ideal gas constant times the temperature, and we're using the ideal gas law for that. We also have F of from 1 to 2, 1 to 3, and 2 to 3, and we're just using that as that was what we had from the previous, from the step-on Maxwell diffusivity equations. So we're using these from that. It just helps shorten it out a bit. So to start us off, we're going to have to import a few things. I'm going to add a line of code to the top. We're going to start off by importing numpy as NP. We're just going to use that as our abbreviation. And numpy is a numerical library. It gives us a lot of functions, so we're going to definitely need that. Next, we're also going to need scipy. So from scipy, we're going to need that for this part. We're going to use scipy integrate import solve IVP. The reason we're using it here is because we're going to be doing differential equations, and we will be needing to use solve IVP. Come on. We also are going to need it for a root finding tool, so we can optimize import root. So that allows us to have a root finding tool. Next, we're going to need to be plotting some things, so we're going to have plotly to help us with that. We're going to have subplots, and we're going to import make subplots, and then we're going to have import plotly graph objects. I'm going to have that as go, just to make it a little bit shorter for us, and that allows us to graph and be able to tell at what point we're graphing at too. We'll be able to see every point. And it allows us to also create scatter plot for this, which is really nice. That's what we're going to be using for graphing. Now, again, we already explained this part, so we have all these givens, and we have here, this is what we found as our estimates for the molar fluxes of acetone and methanol. But we're going to figure out why those don't exactly work right now. So we're going to start off by defining dy, and that's just going to be our function for that. And we need eta as the independent variable, and we're going to use y, but y is the mole fraction. That's going to be the dependent variable. And we're going to have that. We know that y1, and now because Python starts off at 0, it uses 0 as the beginning index. That's where we're going to start. So it starts indexing at 0, therefore we need to start at 0. So we're going to have y1 equals y at 0, y2 equals y at 1, and then y3 is actually, we already know this from the last problem, y3 is really just 1 minus y1 and y2. So we're going to type exactly that. We're going to have 1 minus y1 minus y2. And then we're going to want to put our equation in that we had from the previous problem, and we're going to have it return it as an array. So return, and we're going to use numpy for this. I press caps lock. Array, and have it from y1 times n2, and we had this all in the last problem, so f12, I got 2 of those, f12 minus y3, I think I just got y3 up there, times n1 over f13, and we're going to have down here y2 times n1 minus y1 times n2, and that is all over the f12 minus y3 times n2 over the f23, got that there. And we're going to also have this res as the variable. We're going to solve IDP for that function dy. We're going to have that from 0 to 1 because we have our eta from 0 to 1. And we're going to have it also from the y1i, y2i will be dependent. And the method we're going to use for this is actually going to be called and Bob's just saying rado. I've heard it so many times, still can't say it. But that's going to be the method we're going to be using for this. We're also going to have it as dense output. And this is what allows us to see everything from the exact point. Dense output allows us to see everything to each certain time, which is very nice. And then go ahead and press Shift Enter. Valid syntax. What is the issue that we are having here? I didn't put a colon there. It's always those little things that get you. Just the little things that get you. We're also going to want to, for this sense, we want to define n1i and n2i as just n1 and n2. But we have n1i up here. We're not going to be using those. We're going to be using n1i and n2i. The reason for that is we're actually going to then go ahead and solve down here. Let me go ahead and do that. What is going on there? Oh. It's always those little things that get you. The reason we're going to be doing that is we're actually going to go ahead and solve for 1. And that'll give us this array. But there's an issue with this. These are supposed to be the molar fluxes, but these aren't the molar fluxes, because the molar fluxes should be approaching 0. Since we're solving at 1, that's the eta at 1, they should be approaching 0. These are obviously not anywhere near 0. That one a little bit closer. It's not the same thing. So with that, we don't have that down. We're going to have to change that. So we're going to have is up here. We're going to actually go ahead and remove these because we're going to redefine them. And up here, we're going to define a new function, n. We're going to have it that n1 is equal to n, and this is again because the indexing starts at 0. We're going to have it at 0, and then n2, we're going to have it at 1. And we don't need to do n3 because we already deduced n3 is 0. So we don't have to worry about that at all, which is very nice. And then we're going to also want to move all of this. I press Shift Tab, Control Z. Move all that forward a bit so that it all goes under that definition that we just set. And then on top of that, we are going to want to return that solution that we got there. And the reason why is because we're actually going to go ahead and find the root of this. And the root, excuse me, 1i and n2i. This is very important for us because right here down at the x, the array, those are the values we should be finding. See, you can see those are close to 0, not what we have here, what we got before. So with that, we need to now find these. But how do we do that? Well, we're going to be using that root function to solve for the new molar fluxes. So I'm going to go ahead and set this equal to that res. And we're going to set n1, which we had up here, but we're going to set that now to the res, this function, or this variable, but we're going to have it at x0, which is the beginning of the indexing. And then we're going to have n2, res x1. So that allows us to find these two at those two variables, but we're finding it at 0 and 1 here. And we're actually going to want to then copy this part down here. So we're going to want to redefine that there. I'm going to be using this. And this will all help us for our scatter plot. We're going to be working on that in just a second. These are, again, I don't know why, but, oh, and we weren't supposed to copy this too. But I don't know why this is always ahead. I'm always scared when I press shift enter. It makes me worry that something's going to go wrong. Coding is my favorite. Anywho, so now we can actually finally start off with coding the plot. So we actually got that stuff up here. We worked on it, but we're also going to be needing from Plotly and NumPy. Because NumPy has a, what is it called? A function, a tool, that's right. It has a tool called linspace. And linspace allows us to kind of start off our graph. So we're going to have it from 0 to 1 because those are the parameters of eta. And we're going to have it as 51, and that just allows us to evenly space things out. Now with that, we can also add that we're going to have the solution for that variable is that eta plot. Now with that, we've set that up finally. And these set up the mole fraction values too. So we can actually use this to finally graph out our equation. So we can have fig as our, there's two signs there. Fig is going to be our variable that we're going to be using for the subplots. And thank goodness, again, we have a make subplots. We imported that from Plotly. It's really great what Python can do. So we're going to make subplots. And we're going to have it that there's the rows is 1 and the columns, backwards on everything, it's also at 1. And now with that fig, we can actually go ahead and create these lines, these essentially equations for this. And we're going to have it as add trace. But add trace is really just a way of plot. It's just Plotly's way of doing so. And thank goodness we also have that go, which is the graph objects. Oop, I don't know how that happened there. We have the graph objects there too, which is very nice for us because we can actually make that a scatter. Scatter. And we'll have that the x value, the independent variable, is equal to that eta plot. And we'll have the y value. Now, in this sense, we're going to have 3 different ones because we have it at y1, y2, and y3, which will give us the different molar fluxes. So, we're going to have it that, for this one, we're going to set it that y is equal to the sol at 0. And that is essentially for y1. But we're also going to name that so that we can see it. So we're going to have acetone as that one is acetone. And thank goodness for copying and pasting, we're going to go ahead and do that. That'll make it a little bit easier for us. In this one, we're changing this to 1, because that is for y2. And we're going to change the name of this to methanol. And then we're going to have this forgot we had copy and paste. This one, again, y3 is just 1 minus these two, so we can have that as 1 minus sol 0 minus sol 1 solution. We're just saying that like that. And we're going to change the name for that to air. And finally, shift enter. Ooh, what happened here? I found the issue. It is plot lead. I did not import that correctly. And the other issue that I just found is that I didn't put equals here. The name equals. Finally, that gives us the graph. As you can see, for acetone methanol, it goes down all the way to 0. Air doesn't really have it.